Okay. Uh, in today's class, in okay, now I'm in the PPT mode. So if anything you have to say, whether regarding audibility or PPT visibility, you have to unmute and you have to tell to me. Okay. Now, uh, today's topic is address and name management in wireless sensor networks. Now, actually, why this topics becomes important? Address and name management, because now in the wireless sensor network when we speak, we have some finite number of nodes. Okay, that finite number can be small or large, but finite number. So in that, whether my question is whether should I address the each node randomly and independently, or should I, while addressing, should I like it is relative, well, like should I take any one node as a reference and allow, with respect to that should I address the second one. So that addressing uh, of the nodes, okay, is a very important concept, because if the proper addressing is not done, then the nodes, okay, while transmission it will get confused, okay, and the data may end up in the wrong destination. So to minimize that, okay, so addressing becomes very important. Now, since this is not inter networking, it is just wireless sensor networking. Okay, the addressing scope, okay, can be limited to like MAC protocol. It need not be like since just though it is a multi hop is allowed, okay, but not too many multi hops. So the neighboring region you can consider, and accordingly we can address the nodes. Okay, so it is sufficient that addresses are locally unique. Okay, that's what it need not be globally, just because it is a wireless sensor network. The network is a small one, a finite one. Okay, if you are going for internet, then the numbering, the addressing the nodes will be like sometimes we may have to go globally. So here actually we restrict to it should be locally unique within two hop neighborhood. Two hop is what is two hop? It is like not directly going from source to destination. Okay, or it cannot go because the direct it may be far, or it may be direct connection is not there. Okay, the direct connection is direct channel is not there. So maybe many reasons. So instead of going from source to destination, we are going from source to intermediate node, and from intermediate node to another destination, so that becomes an hop. Okay, so the requirement ensures that no two neighbors of a selected node have the same MAC address. Yeah, the neighbors, okay, should not have the same address. Uh, if you don't have that, then it is called as it is locally unique. That address, whatever you give, is locally unique. Okay. Now, not necessarily we need unique addresses in the WSN for the complete network layer addresses. Okay, for MAC layer, it is sufficient. Since the whole network is not a collection of individual nodes belonging to individual users, okay, but the nodes collaborate to process signals. So we can go for data centric or content based addressing schemes. So there are many addressing schemes are there. Okay, so we'll be going for either data centric or content based. We can go, and like when we see the data centric, see 14 bits are, for example, this is 14 bits are available. So we can address, okay, 16,384 addresses is possible in that, in 14 bits. Okay. See, actually, when we go for addressing, we need to see how many bits we are taking to represent, to address a node. Okay, because we need to calculate the energy spent in sending the address. Okay, the energy spent in storing the address. Okay, energy spent in generating the address. So all these we need to take care. So if you go on increasing the number of bits, then the energy also like subsequently will increase. So that care we need to take. Now, if you, for example, if you're going for 14 bits, then you can address these many nodes. Now, uh, the very basic one is the distributed assignment of network-wide addresses. Okay, distributed assignment. So now this is actually without any prior information. Okay, just randomly uniform distribution of the address is done. Okay, so in this type, now I am not saying that this is the one which is adopted, because later we'll come to know that we need to find out, okay, what is the when we are going for any type of addressing. Okay, we need to see what is the probability that two nodes got the same address, two nodes getting the same address. If that probability is more, then we need to discard that algorithm. Okay, so we need to improvise that. So this is the actually basic one, where we are not using any particular method, just randomly we are considering the 14 bits. Randomly we are allocating or deciding the address of the node. Okay, so suppose we have k nodes, and each of these nodes picks uniformly, independently, okay, address from 0 to 2 to the power m minus 1. Then then what is now 2 to the power m is nothing but n, that is the number of nodes in the network. So what is the probability, okay, that the second node, that is the two nodes are having the same address. Now, so for k is equal to 1, this probability is 1. For k is equal to 2, okay, the probability is n minus 1 by n. Okay, so this is just if k is equal to 2. Now for k is equal to 3, it goes on. So if you see in general, we get, okay, this is the probability. Okay, now with this equation we can reduce and we can write it in this way. Now if you take k is equal to 275, okay, so 275 k if you take and if you substitute here, okay, you find that the conflict probability is nothing but the probability that more than one node having the same address. More than that, is that means what, the addresses allocated are not locally unique. Okay, is more than 90%. And those in 14 bits, if you are addressing only 275, okay, then the percentage is only 1.7, because in 14 bits you could have addressed 16,300 and odd. In that you are addressing only 275. Okay, 275 nodes, out of which 275, more than 90%, okay, have the probability of repeating the same address. Okay, what is the use in repeating the same address? So this is a failed algorithm. This algorithm as such we cannot use. Okay, we may have to do some changes. Okay, then we can use it. Now coming to okay, so many algorithms were actually developed, so to address. In that, actually, few are there where the like what we had. One second, the overhead was there, right? We have studied that overhead. When we studied, actually, overhead is what? It over sorry, not overhead. Overhearing is the unwanted signal is heard by the neighbor node. Okay, unwanted signal is heard by the neighboring node. So that actually we tried to minimize in the previous algorithms. Okay, because the energy, we were considering only about the energy. Now actually in considering the address, okay, we need to consider that at least the neighboring nodes should get to know, okay, the signal passed to this node, so that the control signals or sync signals, okay, so that it will be aware that what address is being allocated to one node. Okay, so the neighboring nodes will come to know that okay, this address is allocated to that. When that node has to be addressed, okay, that algorithm can be written to reject the address by the node if the same thing is repeated. Okay, so like that, one after the other, that improvisation in the algorithm can be done and addressing can be made successfully, but not if the number of nodes are high, then not 100% addressing, like locally unique addressing can be done, but we can improvise on having a locally unique addresses. Okay, next coming to routing part. Okay, the important one is the routing part. Now, actually, coming to what is routing? Now, routing is from source node. If you are taking it to, if you want to send it to the destination node, then actually it can have many path. It can have many path. Okay, the shortest path is directly from source to destination. But what if that shortest path is not existing? Okay, direct path is not existing. Shortest in the sense the direct path is not existing. Then actually I have to go for multi hop, maybe single hop or double hop. Okay, like that. I'll generalize it as multi hop. So in while selecting that, maybe if see from source yes to reach destination D, I have some five paths. Okay, yes to A to B, B to D. Okay, yes to X, X to Y to Z, Z to D. So like this, I have different paths. So in among those paths, which one to select? Okay, that is the concept of routing. That is the concept of routing. So there is no hard and fast rule that routing has to be in this way, routing has to be in that way. Okay, so it is depending on the requirement and specification given. Okay, the algorithm can be selected for routing. See, some may be requiring the time is very important. So the shortest time taken path is considered as the optimum path, best path for routing. Okay, for some more application, the cost is important. Okay, so for cost, okay, actually how to calculate the cost if you ask me, from each for the each link, okay, the weightage will be given. Okay, weightage will be given. That weightage actually you can that is a cost. Okay, you can take it as the amount, okay, required to travel from travel in that link, or it is the energy used for a data bit to travel in that link. Okay, or the time taken for a bit to travel in that link. So like this, okay, many parameters I can go on assigning to that particular uh, parameter, which I use it in the uh, that weight what I give to that link. Okay, so that is actually routing. So depending on our requirement, we take a particular path, okay, to transmit data from source to destination. Now in the routing you have, okay, energy efficient routing. One topic what you have is energy efficient routing, it is important. So now energy efficient unicast means from one side telecasting. So what are the techniques what we are using? See, now actually whatever we discuss here are the only proposed algorithms. Don't think that these algorithms are only used everywhere, no. Okay, each time the depends on the application, it can be modified. So these are some of the proposed one we will be discussing here. Okay, so in this actually first one, first type could be, now what is my agenda? My agenda is to uh, find out the best path to travel from source to destination. Okay, so in that minimize energy per packet or per bit. So actually now in this algorithm we will be finding the minimum energy considered or minimum energy utilized to travel from source to destination. So whichever path gives me minimum energy, that path I will opt. Okay, so look at the total energy required to transport a packet over a multi-hop path from source to destination. Okay, now sometimes the hop will be only two. Okay, A to X, X to Y, Y to D. Okay, if you want to transmit from A to D, okay, A to X, X to Y, Y to D. But the cost matrix in that link is okay, A to X is 5, X to Y is 5, and Y to D is 5. So total cost units are 15 units. Whereas if you take another cost in the sense, okay, I'll take the energy only now. Okay, cost is now I will map it to energy. So energy required is 15 units. Okay, similarly, you take another path, A to L, L to M, M to N, N to O, O to D. So many are there, but all are having 2, 2, 2, 2. Okay, A to L, L to M, M to N, N to O, O to D. Okay, now it is taking only 10 units of the energy. So though multi hops are more, energy taken is less, so I will be opting that one. So in this algorithm, the present algorithm what we are discussing, such technique is being used. Okay, minimizing the hop count. Okay, routes with few hops might include hops with large transmission power. This is what I said, to cover the large distances. So this is not a good idea if you are going for a minimized energy per packet. See, these are the actually this thing. What is that? Paths. See here, one here. Okay, three hops. If I want to reach from A to H or H to A. Okay, this path if I take one, got it? So only three. But here only two hops are there, but three, three, six, highest. Here actually two, 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 six. If I go here, 2, 2, that is 4, 5, 6. So shortest path would be, or the energy efficient path would be this one. Okay, A to B, B to E, E to H. So in this way, actually, we will be calculating. Next one is maximize network lifetime. I will be looking for a routing protocol which maximizes the network lifetime. Okay, I'm not bothered about the fastest transmission. Okay, I'm not bothered about the cost. Okay, I'm bothered about the network lifetime. So network lifetime means what and all. Okay, one is actually battery life. Okay, second one is, see, it is a network lifetime. I can, okay, network is still alive, I can tell that until the any one node fails. Once the one node fails, then actually my network I need to reconfigure, because I need to reroute all the things other than that node. Okay, so until the first node fails, I can tell that okay, the network is still working successfully. Okay, until there is a spot which is not covered by the network. Okay, the actually this happens when the network is like dynamic, that is continuously moving. Suppose your nodes are moving, mobile or a sensors. Okay, if they are moving, then if you find in the network, if you find any spot which is not covered by any of the sensors or yeah, sensors. Okay, then I'll call that as okay, it is a network has failed. Till then it is working. Okay, or until network partition in the sense uh, actually network partition in the sense, so, suppose the node, okay, one particular node is unable to send to the next node. Okay, unable to send to the next node, but it is now all these happens. Okay, when the nodes are moving, it is connected to the uh, other node which wasn't the part of this network. Okay, this IoT network. So in that case, okay, the network is broken because that node is no more the part of this earlier network. So in such cases also we can tell that network lifetime has come to an end. So I want to take a routing algorithm which maximizes the network lifetime. And as I said, okay, considering available battery energy, this is the much more important one, battery energy, because all these are remotely placed, okay, remotely sensed. The battery, whatever we have, okay, in that only it has to work. So until it works efficiently, okay, I say that my network life is still there. Once that battery, okay, drains, then actually the network will collapse. So in that, in by considering this, okay, the first algorithm would be minimum battery cost routing. Okay, it is not just the sum of available battery capacities along the given path. So this is actually a bit different type, but gives the meaning same. But this is a different algorithm. So the name is MBCR, minimum battery cost routing. Here, uh, it looks at the reluctance of a node to route the traffic. Uh, that means what? Reluctance. It is the resistance. Now, see, it is one and the same as I'm saying that my battery has only 50%. So, 50% it allows. Okay. It is saying like my battery has only 50%. So, 50% it is reluctant to use the battery. Okay. To use the battery. And this reluctance increases as the battery is getting drained. So this is one algorithm. So based on that reluctance parameter, okay, you are finding out the uh, routing path. Okay, as I said, here actually reluctance is measured as the reciprocal of the battery capacity. 50% is full means 50% is empty, right? So that empty part, I'm saying it as reluctance. Okay, then the cost of a path is the sum of these reciprocals, and the rule is to pick that path with the smallest cost. Okay, smallest cost. That means actually I have to select the minimum reluctance path. Minimum reluctance path, what does it mean? Okay, I am selecting the battery with maximum capacity. Okay, among whatever is available, maximum capacity. Okay, next that is one type of algorithm. Next one is minimum maximum battery cost routing, MMBCR. Now this also actually calculates the battery resources, energy in the battery, and okay, this algorithm gives me the optimum routing path. Okay, it selects the largest reciprocal level. Okay, that is the smallest reluctance, and all nodes along the path use the cost for this path. Okay, that cost is added as I have done earlier, and actually it will be counted. Okay, the path with the smallest cost is used, obviously. The next one is conditional maximum minimum battery capacity routing, CMM BCR. Okay, if there are routes along which all nodes have a battery level exceeding a given threshold, then select the route that requires the lowest energy per bit. Okay, so this is actually in the subdivision. Now battery level, okay, exceeding the threshold level, that is the minimum level, then actually it requires the route where minimum energy per bit is required because it has come to the threshold level. Okay, so to ensure one more is minimum variance in power levels. To ensure a long network lifetime, one strategy is to use all the batteries uniformly to avoid some nodes prematurely running out of energy, okay, and disrupting the network. So this is actually very straightforward one. Okay, use all the nodes uniformly, but actually we have studied leech. so many protocols, because though we use uniformly, we say that okay, we are using it uniformly. It is not like in the network all the nodes are working in like a same fashion. Okay, some nodes will be working like will be on, it has to be on only for once in 24 hours, whereas some few more nodes should be on continuously. So in that case, if all the batteries are on uniformly, then actually the one which is on for more duration will be drained very soon. So if any one drains also, the complete network collapses. So that may not be the case, but that is the one direct approach we can call it as. See, what the algorithm, what I'm saying is not the optimum algorithms. These are all just the proposed algorithms. Okay, so if you just go through, you may find that like each algorithm will have some drawbacks, some advantages. So if at all who okay in use when you take, there should be a trade-off. Yeah, you have to see what is required and which is suitable, which algorithm is suitable for your requirement, and it has to be adopted. Okay, now some examples are attracting routes, okay, by redirecting. It uses the idea that nodes can overhear packet exchanges between other nodes. So if the energy required to communicate between two adjacent nodes, X and Z, okay, then third node Y, which will overhear, can decide whether it can offer a more energy efficient route, okay, by breaking the direct communication into two hop communication. Okay, so if Y can attract, then it is like energy efficient. Okay, it can be called as energy efficient instead of sending directly from X to Z. If you find that X to Y, Y to Z will save some energy, then it can be done. The next one is the distance vector routing on top of topology control. Now, a Bellman-Ford type or your Dijkstra algorithm is used to find paths with minimum power consumption in the enclosure graph. Okay, now, so that is actually all used one. Dijkstra you have already used. Like a Bellman-Ford is also that type only. It goes for the shortest path, minimum distance. Next one is the maximizing time to first node outage as a flow problem. So here attempt to maximize the time until the first node runs out of energy. Because once the first node is runs out of the energy, then the network will is collapsed. Given is a directed graph to represent the network. Each link, okay, energy cost to transmit a fixed size packet. Rates of data flow coming from certain nodes, their initial power are known. Now this is also same thing. Here, okay, the heuristic starts out from the intuition to use paths that have a large residual energy, that is, the path where the minimal remaining power in all nodes is the largest. Okay. Now, maximizing number of messages. Uh, this is actually before the network runs out of energy. Okay, you need to you need to maximize the number of messages that can be sent over a network. Okay, so consider the class of network where all nodes transmit with identical power and all nodes continuously have data to deliver to a base station. Okay, the key question is the energy consumption of nodes during the data exchange. Now see here, okay, then actually we need to make a cluster like this. Okay, see now this is the base station. Okay, all are connected to this. Now if you see here, um, this actually is the closest S1. Okay, closest contour. Now here this is the next outermost. Okay, so which is not directly connected, one hop you can see to S2 nodes. Okay, you can see one hop from S1 nodes. S1 nodes are single hop directly connected. Whereas if you come to S3, okay, it is two hop. Okay, base station to S1, S1 to S2, and S2 to then it comes to S3. Okay, if you go to S4, it is again multiple hop, multi hop, S4. Okay, so in this way we can categorize because here actually the energy consumed is less. When it comes here, energy consumed is more. Okay, still more and more because many hops are there, right? So in this way when we consider, actually if the energy is once the data is sent, if the energy is less, here actually it can be boosted and it can be sent to the next hop. Okay, partitioned into spheres, okay, that include all the nodes that are rechargeable from the base station in at most I hops. Okay, most nodes are more than a single hop away from the base station. Okay, so all the traffic has to go through the nodes of sphere. Okay, of S1. They limit the lifetime of the network. So we need now which network for any the inner one S1, that actually has to, that should be on for any transmission until S4 whatever is there. So this has to be on. So here actually the authors, they show that no routing will have an energy efficiency worse than a factor 2 SI minus 1, okay, than the best possible ones. So the farthest one, that is the S4, if it has to reach also, it should be, the energy requirement should be above 2 SI minus 1. Okay, so that actually is it is possible to maintain that to energy, and that is actually used one. Okay, so the next one will be multipath unicast routing. Okay, so multipath unicast routing tries to explore multiple paths from a given source to destination. Okay, so they try to balance energy consumption across the multiple path. Moreover, multiple paths provide redundancy in that they can serve as hot standbys to quickly switch to when a node or a link on a primary path fails. Okay. Now, once, say, among many paths, uh, possible paths from source to destination, one path is identified. Once the path is identified, okay, then the forwarding phase can be dynamically decide which path to choose uh, to choose which path is chosen to transmit the packet. Okay, so among, suppose if you have K paths, among the K path, which one is selected? Okay, and now here what they, when they speak, they intend on the minimum energy only. So with the minimum energy, in which path is efficient, then that path is selected. Then actually forwarding phase that can then dynamically decide the path. Okay. The next one is the sequential assignment routing. Now, computing such a k path, okay, require about k times more overhead than a single path routing, because it is like computing, right? uh, from which all paths are available, you need to compute that. The since the all the channels are there, paths are there, okay, from source to destination, how many possible paths are there? So when you compute, actually it requires more energy. So uh, construct a disjoint where disjoint near the data sink, as the nodes close to the sink are those that likely are going to fail first because of depleted battery resources. Okay, so hence they only require paths to use different neighbors of the sink. So to the destination, or to the destination node, neighboring nodes have to be identified initially, because they are the one which are the like farthest, that is the last but one stage of the multi hop. Now here SAR achieves this objective by constructing trees outwards from each sink neighbor. In the end, most nodes will then be part of several such trees. So like tree-like structure, that is the connection. Okay, starting from one point, then actually all branches. So that will be constructed. The source will select the actual path to destination on the basis of information about the available battery resources along the path and the performance metrics. Okay, now constructing energy efficient secondary path. Thus, the construction of tree is one computation. Then after that, the tree will show how many possible paths are there. Then actually uh, selecting the secondary path is the next agenda. When we build multiple paths, how to construct the secondary path from the perspective of energy efficiency of intermediate nodes while considering the primary path. Okay. So these braided paths are only required to leave out some uh, okay, nodes of the primary path, but are free to use other nodes on the primary path in case of requirement. Okay, all these are. Now this relaxed disjointness requirement results in paths that can stay close to the primary path and therefore likely to have a similar close to optimal energy efficiency as the primary path. So see here, actually, this is the one. Now, if this is the primary source and here is the sink, okay, if this is the primary path, from here, this is a hop, again, this is a hop. Okay, now disjoint paths are, now see here, secondary path is from here like this and it comes here. Now, in the braided path, actually, we will be leaving, suppose see here, leaving this node, okay, and we can have this one, okay, and join. And leaving this node, we can have this one. Got it? So, in this way, in the primary path, whatever nodes are there, okay, that among them, one node will be removed and alternate paths are calculated and kept, counted, and it is kept. So I hope you understood. First, actually, this node is eliminated. So your path would be from here, go here, then come to this node, then this one. Because, okay, this was the path identified as the primary path. Then you drop this one. So your path would be this one, from here, go here, then come here. So this is the second one. Okay, yeah, the braided path has to avoid the next upstream node on the primary path, but is then free to use nodes on the primary path. Okay, next one is simultaneous transmissions over multiple paths. Okay, when using multiple paths as a standby for the primary path, failover might be improved compared to strictly single path solutions. Okay, so anyway you have identified the secondary path. In case okay any disturbance or breakdown happens in the primary path, so the secondary path is immediately used. You don't have to compute once again. Okay, because the secondary path for each node is identified. Okay, so that can be utilized. Okay, there is some delay in detecting the need to use a secondary path. Okay, so while computing for the secondary path, there is a little bit delay. If source, but that is not after the failure, it is before the failure only. If source node alone or some node on the primary path has to decide, then actually overhead is involved. So that, okay, it will be there. Okay. So use all or several of the multiple paths simultaneously, assuming no disjoint paths, and to send several copies of a given packet over these different paths to the destination. Okay, so this I will do it in the next class. Okay, I will stop the class here only. Okay, so now any doubt? Whoever are present, any doubt? You can just type if there is any doubt. Okay, or else you can, I'll end the meeting. You can leave the. Okay, no doubt, right? Fine. Shashank, any doubt?